So let's turn our attention now to weighted graphs, graphs in which edges have costs associated with them. The most important thing that we can do with weighted graphs is to compute shortest paths. So let's review what we have seen so far. So we have been looking at unweighted graphs, that is sets of vertices and sets of edges where each edge is just a connection between two vertices. We have seen two systematic strategies to explore such graphs, breadth first search and depth first search. Now both of these will be linear in the size of the graph if we use an adjacency list representation for the edges. Now we saw that while we explore a graph using either BFS or DFS from a given vertex, not only do we discover which vertices are connected to the start vertex, we can also recover the path back to the start vertex by keeping extra information such as the parent of each node we visit. We observed that breadth first search, because of its layer by layer strategy, actually uncovers the shortest distance to every vertex in terms of the number of edges from the start vertex. And depth first search, though it does not find the shortest path, it gives us a lot of other information in terms of the order in which we visited. So by keeping track of the pre and post DFS numbering, we can actually recover structural properties of the graph. Now we look at what happens if we add costs to the edges. Now depending on the application, these costs have several natural interpretations. For example, in the initial example of a graph, we looked at an airline routing map. So on such a graph, the edge weight, the cost associated with an edge, could be the ticket price on the flight. Or if edges represent roads in a network of highways, then we might have a cost representing the toll that one has to pay on a particular segment of road. Or if we have a railway network, it might represent the distance between two stations. Or on a simple traffic road map of a city, it might represent how much time one might expect to take between two intersections at busy times. So in general, a weighted graph is just a normal graph along with an extra function which tells us the cost of each edge. It's usual to call this a weight function. So a weight function just assigns each edge in E some number. So let's think of it some real number. Right? So now if we have a path from V0 to Vn, okay, so we have a path from V0 to En, we have a sequence of n edges, V0, V1, V1, V2. Each of these in a weighted graph would have a weight, and a natural thing to do would be to add the costs of these weights. Right? So supposing these are distances, then the total distance if we follow this path from V1 to Vn will be the sum of the distances. If it's a sequence of flights, the total cost that we pay for a ticket will be the sum of the cost. Right? So we will extend weights from edges to paths by just adding up the sum of the weights along each path. And now a natural problem that we want to solve is to find the shortest path between a given pair of vertices. That is, what is the minimum cost that I can incur to go from V0 to Vn? So we have seen before that breadth first search will solve this problem if our cost is in terms of number of edges. Another way of saying it is that we can assume that each edge has the same cost, 1 or any fixed number, so that as I traverse more edges, the cost is proportional to the number of edges traversed. But if we don't have this property, if the costs can be arbitrary, then breadth first search does not work. For instance, in this example, we see that between 1 and 3 there is a direct edge, but its weight is 80. And we can do a shorter cost path from 1 to 3 by going via 2. So it has 2 edges, but the total cost is only 10 plus 6, which is 16. Right? So the shortest path in a weighted graph need not be the shortest in terms of number of edges. We are talking about the sum of the costs along the edges. So we might have longer paths in terms of number of edges, but shorter total cost. And our goal is to compute such paths regardless of the actual length of the shortest path. So we can ask two types of questions regarding shortest paths. One is the so-called single source problem. In the single source shortest path problem, we have a designated place from where we start all our paths, and we want to find the shortest distance to every other path. Now this has very natural application. So supposing you are a manufacturer and you have a factory where you make all your items. Now you have to distribute these items across the country. So how do you find the shortest way to transport your items from the factory, which is a single point, to all the places where it can be sold, to all the retail outlets? Or you might be a courier company Now a courier company will ship all items to a given city to a centralized office, and from this centralized office it has to be distributed to all parts of the city. So how do you compute the shortest path from the distribution office to all the different addresses to which the courier items have to be delivered? Another problem would be to compute the shortest distance between any pair of cities or any pair of vertices. So this would be a natural problem, for example, if you have a routing network of an airline or a train network. Now whenever you want to travel from city A to city B, you would like to compute the shortest path between A and B. For instance, if you use a service like Google Maps and you say that you want to go from a source to a destination, it will try to compute the shortest path and give you the time in terms of walking, driving, etc. Right? So we have two different types of problems. One where we have the single source and we want the shortest path to every destination but only from that source, and another version where we want to find the shortest path between every pair of vertices. So we will begin by looking at the single source shortest path problem. So we have to designate in such a problem what is the start vertex. So maybe our start vertex, let us by convention assume it is the vertex 1. Remember that we usually call our vertices 1, 2, 3 up to n. So here we have a graph with 7 vertices and the edge weights are written by the side of the edges in red, and we want to start at 1 and find out how to get from 1 to every other vertex in the shortest possible cost and a systematic way to compute this. So here is an analogy which will help explain the algorithm. So let's assume that every vertex is an oil depot and all the edges are pipelines, and the pipelines the costs are the lengths of the pipeline. Now when we set fire to this original vertex, start vertex 1, a fire will catch on all the pipes connected to vertex 1. Assuming that the fire travels at a uniform speed, right, it will reach the closest vertex first. Right? So the first oil depot that catches fire after the first vertex is the nearest vertex to 1. Then the second oil depot that catches fire is the second nearest vertex to 1. And assuming this fire is traveling at a uniform speed, by measuring the speed at which the fire reaches each vertex, we will actually end up computing the shortest path. So let's try to execute this analogy, this strategy on this particular algorithm. Right? So we begin by setting fire to the source vertex at time 0. Right? And now a fire will start going along the edge 1, 3 and the edge 1, 2. Now since the edge 1, 2 is shorter, in 10 units of time vertex 2 will burn. At this point we have indicated by the fact that there is a small burnt portion here that there is a partial fire going from 1 to 3, but it has only traveled 10 out of 80 units. Only 1/8 of the way it has traveled from 1 to 3. So at t equal to 10, vertex 2 burns, and we can say that this is the shortest cost or the shortest distance to vertex 2. Now the fire continues to propagate through 2 in two directions, right? From 2 to 3 and from 2 to 5. And meanwhile, of course, the fire from 1 to 3 also continues in the same rate as it was before. Now we can see that after 6 units of time, vertex 3 will burn. Right? So at t equal to 16, vertex 3 has burned. Now this has, the fire from 1 to 3 has traveled 16 by 80 of its distance. That the fire from 2 to 5 has traveled 6 by 20 of the distance. Right? Now having burnt 3, a new fire will continue in this direction. This old fire from 1 to 3 continues as before. And of course the fire from 2 to 5 continues as before. So now we have to see which of these will reach its destination first. So we can see that the fire from 2 to 5 has, in 14 units of time, will reach 5, by which time neither 3 nor 4 would have burnt. So if we continue another 14 units of time, at t equal to 30, we find that vertex 5 burns. And here we have done 14 out of 70 from 3 to 4. And we have done 30 out of 80 totally from 1 to 3. So these fires are still on their way from the source, the starting point of the edge to the ending point of the edge. Now continuing in this vein, the fire now propagates from 5 to 6 and 7, and you can see that in 10 units of time, we will find that vertex 7 burns. Okay? And now from 7, a new fire starts towards 6. There's an old fire coming from 5 to 6, but this will overtake it because this has only done 10 by 50, so there is still 40 units of time to go before the fire reaches 6 from 5, but in 5 units of time it will reach from 7. So therefore at t equal to 45, we find that vertex 6 burns. And now the only vertices which are remaining to burn are actually 3 and 4. Right? So at this point, if we continue, we will find that at t equal to 86, actually sorry, vertex 3 had already burned. Though this fire had not reached it, vertex 3 had burnt. The only vertex remaining to burn was 4, and at time 86, that is 70 units after the fire started at the beginning of the edge, right? It finally reaches, and now everything is burnt, and now we have labeled each vertex by the shortest time it took for the initial fire to reach them, and this we claim is the shortest path to each vertex from the start vertex 1. So let's see how we would actually compute this burning process that we described. So what we do is we associate a time to the shortest distance as a quantity with each vertex, and initially we don't know anything, so we assume that the vertex is not reachable. That is, the shortest cost to every vertex is infinity. Now we know that the vertex 0, vertex 1, the start vertex is reachable in no time at all, so we assign its cost to be 0. And having assigned its cost to be 0, we can now recompute its neighbor's cost as the minimum of the cost that you can reach through 1 and the cost that we already know. So from 1 to 3, we can go in time 80, we believe right now it's infinity, so we know that we can improve the infinity to 80. Similarly, we can improve the infinity of 2 to 10. Okay? So in this process, we get 2 updates. Now all the other vertices, we still don't know how to reach them, so they don't get changed. Now among these two, we find that 10 is smaller than 80, so 10, now there can be no shorter path to 10. So we say that 10 is burnt, and we update its neighbors again. So we say that vertex 2 burns at time 10. Now because it burns at time 10, we can update the cost to 3 as the minimum of 10 plus 6, 16, or 80, which is 16. And now we can reset 5 from infinity down to 10 plus 20 is 30. So we continue in this vein, now using the fact that now among the things that are going to burn, 3 is going to burn at 16 and 5 is going to burn at 30. It's clear that 3 burns next. So we reset its status to burnt, and we update its neighbor, namely 4, to 16 plus 70 is 86. Now among those which are not burnt, namely 4 and 5, which have a finite value, 5 will burn next. So we set its status to burnt, and we update its neighbors to 80 and 40. At 6 we have 80, and 7 we have 40. Now 7 burns next, so we now look at the costs going out of 7, and we replace the 80 at 6 by 45. And now 45 burns next, 6 burns next at 45, so we mark it burnt, and finally we mark 4 burnt at 86. So to write this formally as an algorithm, we maintain this information about burnt vertices and the time it takes to burn a vertex in 2 different arrays. So we have an array called burnt vertices, which is a Boolean array. So it tells us whether a vertex has been burnt or not. And then we have an expected burn time array, which tells us the time at which a vertex is believed to burn. So initially we said that no vertices are burnt, so we set all the vertices to have burnt vertex value false. And initially we set the expected time for every vertex to infinity. Now infinity, of course, is a concept which is difficult to estimate, but we can easily check that no vertex can be at a distance which is bigger than the sum of all the costs in the graph plus 1. Right? Because at most you can actually, the shortest path will actually take even fewer edges, but at most you can use every edge. There's no point in using an edge twice. At most you can use every edge once. So if you add up all the costs in the graph and add 1 to it, then this can definitely be treated as infinity. No actual cost can be larger than this cost. Okay? So we can use infinity, but for infinity there is a concrete strategy to assign infinity. Now we start with the source vertex, which we assume is 1, set its expected burn time to 1, and now we repeatedly look at the smallest expected burn time, burn it next, and reset the expected burn time for all its neighbors based on the current burn time of that neighbor and the minimum of that and the value of the burn time through this vertex. Okay? So this is a very simple algorithm. So here it is in pseudocode. So we have these 2 vertices burnt vertex array, and we have the expected burn time array. So we initialize burnt vertex to false and expected burn time to infinity for all vertices. Now we set the source vertex expected burn time to 0, and now we choose the smallest unburnt vertex. So we look for a U which has not been burnt and whose expected burn time is minimum, make it burnt, right? And for each of its outgoing neighbors which is not burnt, if the current estimate for that is bigger than the estimate of going through U, that is the burn time of U plus the wait from U to B, then you update the burn time of B to be the new one. So in our actual algorithm, burnt and expected burn time have a natural interpretation. So burnt is just visited. So when we have visited a vertex, we have burnt it. And the distance is just the expected burn time. So we can just rewrite exactly, this is the same algorithm. Okay, it's just that BV has been replaced by visited and EBT has been replaced by distance. Right? So we set visited to false, distance to infinity, start with the initial distance to the start vertex is 0, and then it repeatedly for each unvisited vertex with minimum distance, set it to be visited and update its neighbors. This is Dijkstras' algorithm for single source shortest paths